All right, hello chemistry class. We are looking at our next chapter here, and we're going to be studying a little bit about thermochemistry. Now we've touched on thermochemistry before, because all it is we're just talking about the heat exchange that is involved in chemical reaction. Thermo here actually is our prefix that signifies we're talking about heat exchange or heat transfer. Okay, so the first thing you can put in your notes for this chapter 16.1, chapter 16 here, is you can put down thermochemistry, this definition right here. Thermochemistry, we are going to be looking at the transfer of energy, specifically heat energy, as it's involved in chemical reactions and physical changes. Okay, physical processes and chemical reactions. So please write down the definition here for thermochemistry. Okay? Now, one thing that we do have to differentiate when we're talking about thermochemistry is this notion of temperature versus heat. They're definitely related, but they're not the same thing. Okay? So the next thing I want you to put down is temperature. We need to understand what that is. It is a measure of the average kinetic energy of all the particles in the sample of matter that you're working with. So, what is kinetic energy? Kinetic energy, let's write this definition down. Kinetic energy, KE, is 1/2 times the mass, m, times the velocity, v, squared. So this is your mass here, m. The v is velocity. And you can see that the larger particles, mass is involved here, larger particles traveling at the same speed, the same velocity as smaller particles, are going to have a greater kinetic energy. But also, the speed here, the velocity, is squared. So as particles increase their speed, their velocity, their kinetic energy is going to go up exponentially because that value is squared. Okay? So kinetic energy is really what we're measuring when we take the temperature of a sample of matter. We're measuring how much kinetic energy do those particles have. They all don't have the same kinetic energy. Some are traveling faster than others. If you had a pure substance, they all going to have the same mass, all the particles, but they may be traveling different velocities. But the average kinetic energy would give us that temperature. And obviously, how that's related to heat is if you pour more heat energy into a sample of matter, then the temperature is going to go up. Why is that? Because you're going to increase the velocity of those particles. That V is going to increase, therefore increasing the kinetic energy, and that's what we're measuring when we measure temperature. Okay? Now, one thing that we've talked about before is the notion of our different measurements for temperature. We have Fahrenheit, F, we have Celsius, C, and we have Kelvin here, K, which is often used in chemistry. Kelvin is going to be our temperature that we often refer to, and to find that you take the value of your temperature in Kelvin and you add 273. Okay? So you will not see Fahrenheit in chemistry very often. You will see Celsius and now Kelvin, which is just 273 plus the Celsius. Okay? Now, how do we measure the exchange of heat? We basically use what is called a calorimeter. A calorimeter, you can see that word meter here. Meter is like to measure. Calorimeter, calories, you think of heat energy that's stored in your food, for example. That's a form of heat energy. And it measures what? The energy absorbed or released when we have a chemical or physical change. Okay? So a calorimeter is a device that is going to measure this heat exchange, this heat transfer. Okay? Some other definitions here. Heat, obviously, it is a form of energy. You should write this down. This is a form of energy that is transferred between samples of matter. And yes, they're going to have different temperatures. So heat is going to flow from what? Because of the difference in temperatures, it's going to flow from high temperature to low temperature. It's always going to flow from high temperature matter to low temperature matter. Okay? The unit that we use for energy, specifically here for heat energy, is called the joule. Okay? And a joule is, and we really haven't talked about this unit here, Newton, but a Newton is basically a unit for force. Okay, force, and then meter here is distance, so it's what force is exerted over what distance. And that may sound kind of odd when we're talking about chemical reactions, but that's what's happening. This energy here, this joule, the joules here, that is a certain amount of energy that's being transferred during a chemical reaction. Okay? We're going to focus on heat energy during these reactions. All right? Now, let's talk a little bit. Let's make this a little simpler instead of just talking about a reaction right now. We've talked about actually reactions before and the heat that is involved. We've talked about exothermic reactions and endothermic reactions. And we looked at diagrams that showed the heat starts at a certain point, and if it ends higher, then it absorbed energy. We know that absorbed energy, and that is endothermic. Okay? That's an endothermic reaction. If it's ending higher, the energy of the particles ending higher than it started. That's endothermic, absorbed energy. If the starting energy is higher than the ending energy, then that's exothermic. It gave off that energy. The energy here dropped down. Okay? Here the energy of the particles went up. So endothermic is entering or going in, being absorbed by the substance, by the particles. Here, exo means you lost energy and it was released into the environment, into the surroundings. Okay? But let's focus just a little more simply on just an object gaining or losing heat. Okay? So here we're heating up a bar or a cylinder of metal. In this case, I believe it is brass. Yep, this is brass here. We heat this brass up. Obviously, those particles are going to be gaining kinetic energy. They're not going to be moving a lot. Obviously, it's a solid. They're kind of fixed in place, but they're going to be really vibrating with greater energy. The kinetic energy is going to be greater. The temperature of that's going to go up. Then we take that brass cylinder and we put it into a beaker of water. And that beaker temperature, the water's temperature is going to go up from 21 up to 35. Well, what happened here? The heat transfer went from the brass to the water. We heat the brass up. It now has more heat energy than before, and we put it into the water. And remember, heat flows from high temperature to low temperature. So the brass is going to transfer some of its heat energy to the water, and the temperature of the water goes up. Some substances, here we have brass, here we have water, some substances absorb energy really, really well without changing their temperature very much. Other substances absorb energy and their temperature changes dramatically. Okay? That property is called specific heat. Okay? Specific heat. So we're actually going to talk about the specific heat of some different substances. And you can see there's a whole list of substances here, and you're given their specific heat values over here. Let's look at the units here. What is this measuring? If we say that the specific heat of water, that's liquid water, see the L? Liquid water is 4.18, and look at the units, joules per gram Kelvin. 4.18 joules per gram Kelvin. What does that mean? It means for every 1 gram, it's going to take 4.18 joules. It requires 4.18 joules of energy to do what? To raise the temperature 1 Kelvin. Okay? So if you want water, if you want 1 gram of water to raise its temperature by 1 Kelvin, then you're going to have to put in 4.18 joules of heat energy into that sample, that 1 gram of water. That's what it means. That's what the specific heat means. And notice these values differ. 4.18 is fairly large. Look at, compare to other values here. Look at ammonia, only 2. Some different liquids here, benzene, ethanol. Here's some metals, aluminum, copper, gold, really low. They change their temperature pretty quickly, even just with a little amount of heat. These are low amounts of heat that are going to change a gram of copper or gold or iron by 1 Kelvin with just a little amount of heat compared to the 4.18 up here. So water's, here's the key, listen, listen, listen. Water's temperature does not change as dramatically as other substances when you add heat energy to it. That's the point. Specific heat is measuring how quickly does or how much does the temperature go up by when you add heat to that substance. Does it go up a lot? Does it go up just a little bit? And water can absorb a lot of heat. Look at that, 4.18, absorb a lot of heat without changing its temperature too dramatically. Okay? These temperature changes depend on what? The nature of the material, the mass of it, and the amount of the temperature change. So we have a formula. If we take these things into consideration, then we have a formula. Okay, and here is a very important formula that we're going to be using in order to find out the amount of heat that is exchanged or transferred. Okay, here are the values that go into that. Q is going to represent energy, heat energy, gained or lost. That is Q. Q is going to be heat. And then this C sub P, that is actually the heat capacity, or I should say the specific heat. It's these values up here. These values up here for whatever substance you have. You'd have to be told what substance it is. So this C sub P is the specific heat. Okay? C sub P represents the specific heat. M is the mass. Remember this units here? Look at the units. It was per gram. So mass is going to influence how much the temperature goes up by, or the amount of heat required to raise the temperature. So this is mass, and then delta T is the change in temperature. Look at the units here. CK, Kelvin. All right? So this formula right here, I'm going to write it again. Q equals, and I'm just going to put a C there. Okay, I don't need a C sub P, but you understand. C M delta T. Okay? Now I might refer to this as Q equals C mat. See this delta here kind of looks like an A to me, so sometimes I just say C mat. Or this C might be an S. Okay, sometimes they use S for specific heat. Okay, so I might say S mat. Okay, it's simply Q is the amount of heat, C or S, whichever variable you prefer, is the specific heat for that substance. M is the mass, delta T is the temperature change. You have 3 variables here. Okay? Actually, we have 4 variables because delta T is the change in temperature. So let me rewrite this. Delta T is the final temperature, T sub F, minus the initial temperature, T sub I. So there are really 4 variables here. Sometimes the problem will tell you what the change in temperature is. Sometimes they'll tell you what the mass is. The specific heat is a fixed value for every substance. But sometimes you might have to find the final temperature or the initial temperature. So you have to break that delta T apart into final minus initial. Okay, let's look at a sample here. We have 4 grams. There's your mass. Here we write it down. 4 grams is your mass. Sample of glass. This is glass now. Now we're told what the material is. And it was heated from 274 to 314. Notice the unit here for temperature is Kelvin. So we have initial and final temperatures. Okay, so that increase here, obviously the delta T is 40. It went up. increase, positive 40. And was found to absorb, this is now your energy. That's the Q. You're told what the Q is. You're actually told the Q value here. That's the amount of energy that was absorbed. They're asking you to find the specific heat of this particular glass material. Okay? So in our formula, Q equals Cm delta T. You're given the delta T, you're given the mass, and you're given the Q. And you're asked to find the C value. So you can rearrange this and solve for C if you want. I'm basically going to divide both sides by the mass and the delta T. And my C is going to equal the heat divided by mass and delta T. And that's exactly what they have here. So just plug in those values now. Your Q, we were told, was 32 joules. Your mass is 4, the delta T is 40. Plug it in, and there is the specific heat capacity for that glass material. What does this mean? 0.2, it's going to take 0.2 joules of heat energy added to the glass, added to 1 gram. I know we had 40 grams, but this is now per gram. Oh, sorry, we had 4 grams. This is per gram to raise it 1 degree Kelvin. Okay? Because it took 32 to raise it 40 Kelvin, 4 grams 40 Kelvin. So that's why we're dividing here. It's going to then therefore take only 0.2 joules to raise it 1 Kelvin for 1 gram. Okay? And then what they're asking here in the second part of this is how much energy will the same glass sample gain when it's heated from 314 to 344. Now we have a new delta T. All right? Now we're trying to find Q. We're going to take the value from our previous step. Now we know the specific heat capacity, the same mass, but now the temperature change is 30. It's going up only 30. And how much heat is going to be required? Well, we take our specific heat capacity times the mass times the change in temperature, and it's going to require 24 joules of heat energy to do that. Okay? Okay. Now, I actually am going to pause this video, stop for chapter 16 right there. We have some other aspects in this chapter about heat energy, but this video is only going to focus on right now just the specific heat capacity and this formula right here. Okay? Now I'm going to see if I can find another sample just so we can do another example problem here using this particular formula. Okay? Okay, here's one. It says how much energy would be absorbed as heat by 75 grams of iron when heated from 295 to 301. Well, let's just use our formula. Q equals C mat. What are we given? We're told the mass is 75 grams. Okay? And we have change in temperature. Our delta T, it's going from 301, sorry, it's going from 295 up to 301. So 301 minus 295, we have a 6 Kelvin increase in temperature. 6 Kelvin. Now this is iron. So if we look back up at our chart here for the specific heat capacities, iron, I believe, is on that list, and we just are going to take that value right there. Iron is 0.449 joules per gram Kelvin. And we're going to use that in our formula, 0.449. Oops, sorry. There we go. So our C is 0.449 joules per gram Kelvin. Okay? Just plug in the values because we're asked how much energy would be absorbed. That's the that's the Q value. So all we do is we put in our C, 0.449 joules per gram Kelvin times 75 grams times 6 Kelvin. Look at the units, by the way. Do you see that the grams cancel? Kelvin cancels, and we're going to have our answer in joules. So on your calculator, you just take 0.449 times 75 times 6, and you would have your answer in joules. That's how much heat is absorbed to take 75 grams of iron and raise the temperature from 295 Kelvin to 301 Kelvin. Okay? All right. So that is specific heat capacity, and using this formula to find out the energy, the heat energy absorbed, or it could be lost, heat energy gained or lost. And I'll just say one last thing here. In our example up here with the brass cylinder, the amount of heat that is gained by this water, the amount of heat gained by the water is the same as the amount of heat lost by the brass. The brass loses that amount of heat, the water gains that amount of heat. Okay, assuming it's not lost to the surrounding area. Okay? All right. That is really just what I want you to know from this section right now, and we'll pick up more in the next video.